This video is going to be about enthalpies of formation, and it's based off Hess's law. All right, so standard enthalpies of formation are the amount of enthalpy or heat needed to produce 1 mole of that compound from its naturally occurring elements. So for carbon dioxide, it would be carbon solid and O2 gas. And for carbon monoxide, it would be carbon solid and half a mole of O2 because it's only for 1 mole of it. So you wouldn't balance the reaction to give you 2 COs so that you have 1 whole O2. It would be half an O2 to give you 1 CO. Okay, and so the reason why I talk about that is because, like, the standard enthalpy of formation, that's what this little F means, for oxygen is 0 because it can't be formed from a naturally occurring element because it is a naturally occurring element. Okay, so anything that's naturally occurring has a standard enthalpy of formation value of 0. There's an equation for it, and it looks complicated, but it's really not. The change in H, okay, for a reaction is equal to the sum of, right, that means sum, the sum of the change in enthalpy of the products times their moles in the reaction minus the sum of the change in enthalpy of the reactants times their moles from the reaction. And so the little degree symbol, that just means that those values were found at standard states. And so standard states, pressure is 1 atm, any concentrations are 1 molar, and the temperature is 298 Kelvin or 25 degrees Celsius. You really don't have to worry about that right now, but in the next unit in thermodynamics, it plays a bigger role. So you might as well learn those values now. All right, so there's 3 examples that I want to do, and if you have to do these on your own and you're not given the values of delta H, they can be found in the appendix of your textbook. There's a huge table. All right, one thing that you have to be mindful of are the phases that things are in, because you might have multiples. So like we have liquid water and we have gas water, and they have 2 different values. All right, so the delta H of formations for these are in kilojoules per mole. And they're all found at under standard conditions. That's why they have that little degree symbol. Okay, so for the first one, we have ozone. So I'm going to number these 1, 2, and 3. So for the first one, ozone has a value, it's right here, of positive 142.7. So I'm just going to write them underneath. Nitrogen monoxide gas is 91.3. Nitrogen dioxide is 33.2. And O2 is 0. Right, because it can't be formed. It doesn't have a formation value. It can't be formed from its naturally occurring elements because it is a naturally occurring element. The delta H of a reaction can be found by taking the sum times the moles times the delta H of formation of the products minus the sum times the moles, the delta H of formation of the reactants. Okay, so it's always products minus reactants. Final minus initial, because the products are final, the reactants are initial. For number 1, I would take 33.2, so we have 1 mole of NO2 in that reaction, and there's 33.2 kilojoules per every single mole of NO2. Okay, so that's all of my products because oxygen is 0, and then we're going to subtract from that 1 mole of NO, because there's only 1 of them, for every 91.3 kilojoules per mole of NO, plus 1 mole of O3 times 142.7 kilojoules per mole of O3. So I'd have 33.2 minus 234 kilojoules, and I end up getting negative 200.8 kilojoules for that reaction. So the delta H for this reaction would be equal to negative 200.8 kilojoules. All right, so number 2, and I'm going to just write them underneath the reaction. So sulfuric acid liquid is negative 814. H2O liquid, not gas, so I don't want to use this one. I want to use the one above it, is negative 285.8. And then sulfur trioxide is negative 395.7. So for the second one, I'm going to take 1 mole of H2SO4 times negative 814 kilojoules per mole, And that's so the mole cancels out, right? So we can add them together. And then negative 285.8 for 1 mole of water plus 1 mole of SO3 times negative 395.7. And that is a very common mistake when you don't have 1 mole to forget to multiply by that. So try not to do that. All right, so we get negative 814 here minus negative 681.5. And so that's going to give me negative 132.5 kilojoules. So that's my delta H for this reaction. Okay, so I'm going to erase everything that I have written because I'm going to show you something with this last one. Okay, so 2 NO2s, so it's 33.2 per kilojoules per mole. Oxygen is 0, and nitrogen monoxide is 91.3. All right, so if we just do the equation the way we've been doing it, we would have 2 moles of NO2 times 33.2 kilojoules per every single mole, minus 0 for the oxygen, plus 2 moles of NO times 91.3 kilojoules per mole. Okay, so we would get 66.4 and 182.6. So when we subtract them, we end up with negative 116.2 kilojoules. So the reason that this works and where the equation came from to begin with is because if I were to write all of my enthalpies of formation for these reactions, what I would have is I would have N2, 1/2 N2 plus 1/2 O2 makes 1 NO. And the delta H for that is 91.3. Okay, because that's the formation. It's the formation of 1 mole of NO. And then I would have 1/2 N2 plus O2 goes to NO2. And the delta H of formation for that one is 33.2. Now, if this is the reaction that I want, what I would have to do is multiply this bottom one by 2. So this would get multiplied by 2. I would get 2 of these. I would have 1 and 2 because 1/2 times 2 is 1, and 2 of these. Now NO would have to be flipped. So the sign would change for this, and it would be multiplied by 2 because we need 2 of them, 2 NOs. So this one gets flipped, so I'd have 2 NOs goes to 1 O2 because we're multiplying everything by 2, right? We're multiplying it all by 2, and 1 N2. And we would have for that delta H 2 times 91.3. And we changed the sign for the reactant. So this is gone. So we have negative 91.3 times 2 now for that. So the N2 would cancel out, and one of the O2s would cancel out because we have 2 O2s on the reactant side, 1 O2 on the product side. So to have 2 NO plus O2 goes to 2 NO2s. And so then if we add these together, we end up with the delta H for this reaction, which would end up being this value right here. Because we flip the reactants, that's why we have this negative sign. That changes the sign for the reactants because they're not products anymore, they're reactants. And these 2's come from having to multiply by N, so it comes from that right there. So that's just a little explanation if you wanted it. If you're given the enthalpies of formation, I expect you to use the formula and just plug them in and get your value out. Just don't forget to multiply by the coefficients.